The next step was to take this insoluble fraction at pH 1.4 and increase the pH to 2.8. Now something happened. Some part remained insoluble, and that insoluble fraction had about 90% G and still high dP. And the other, which became soluble, had 90% M, roughly. So now you see the pattern. We have a fraction with about 50% G, and which is of the Mg type, the G type and the M type. So from that moment on, it was understood that alginate contain 3 types of blocks, which you can isolate by this method. And in all research papers after this discovery, we find descriptions like this. That the chains contain M-type, G-type, and also Mg type, it should be. But we don't know where in the chain the blocks are. This was published in 1966. So then we understood that alginate is a very complex type of molecule with a kind of modular structure. At that time, nothing was known about epimerase. Epimerase was discovered later, a couple of years later, in fact. And it was thought that alginate was made by sequential addition of sugars, one after the other. But how was it regulated? It was not understood. But a couple of years later, when we finally got the epimerase from bacteria, the picture that I showed you already became clear. So that was an extended repetition of what I talked about last time. So let's just move on. The epimerization of M into G has big consequences. And this is the explanation. So this is mannuronic acid like it looks from a conformational point of view. Most of you know that sugar rings are not flat, but they have a chair-like, or in some cases, boat-like structure. This is, of course, because of the carbon atoms having the classical 109-degree angle. So if you try to make a 6-ring, whether it's a sugar or cyclohexane, you end up with a chair or a boat. And this is the most stable form of mannuronic acid. It's called 4C1 chair. C means chair, like you sit on. So, like these chairs you sit on. 4 up here means carbon number 4 is on the top side of the plane. If you can imagine a plane from O to C5 to C3 to C2, this carbon number 4 is on top and carbon number 1 is down. So it was decided to call this 4C1. So mannuronic acid is 4C1. Also glucose and galactose and mannose are 4C1. But when the enzyme comes, and what the enzyme is doing is to switch configuration at carbon 5 so that the carboxylic group now points down. This structure is unstable because of steric conflict. The carboxyl group comes too close to other groups, so it's unstable. And what can it do? It will flip over to another chair conformation which is called 1C4. A little difficult to see maybe, but this flips down and this flips up. And now I have rotated a little bit. So if you imagine you take this little back like this, you see that carbon 4 is on the downside and carbon 1 is on the upside. Can you see that? Yeah? So that is the first consequence. And the next consequence is for the whole polysaccharide chain. This 4C1 to 1C4 transition has immediate consequences for the geometry of the chain. Because I made this fragment, MMGG, we use as example. The M in the 4C1, this and this, tend to form a very stretched structure. You may note that this sugar is flipped 180 degrees. Can you see that? This oxygen now is on the front side. This is carbon 1, this is carbon 2, 3, and 4, 5, and 6. And this is almost identical to what you find, for instance, in cellulose. Cellulose, we know exactly, is built in this way. And the same basic structure is found between 2M. So, therefore, the linkage between 2M, we call it di-equatorial, because this direction is called equatorial. And this direction, where there is a hydrogen, which we usually don't write it, but it's axial. So this linkage from here to here is equatorial, equatorial, this way. But if you look at the Mg, this one is still equatorial, but this one is axial with reference to the direction of the sugar. So this is x, and so on. You can see that if you go from a G to an M, it will also be axial this way and equatorial this way. So Gm is x. And finally, the most interesting part is between 2G, because this linkage is axial compared to this direction, and this linkage is also axial compared to the direction of the sugar. And as a consequence, you can see that G's after one another form a U-shaped structure. Whereas the M's make an extended flat structure. And inside this structure, interesting things can happen. What do you think can happen here? What do you think? Maybe calcium can bind here. We will look at that. First, we know this is true also because of X-ray diffraction studies done about 30 years ago. So because of this transition from 4C1 to 1C4, this distance gets shorter. The chain kind of becomes shorter. So we get a different repeat, and such repeats are very easy to detect by X-ray. So this is true, we know that.